Hello, everyone, and welcome to this Curious About Live session brought to you by Glasgow Science Centre. My name is Patrick, and our guest today is James Fawcett, who is an outreach coordinator for the Euclid Space Telescope at the University of Edinburgh. Today, we're going to hear from James about space telescopes and the universe. We're going to discover why space telescopes are important, how we are mapping 1/3 of the sky, and the role Scotland is playing in this mission. As you're watching this session, I'm sure you're going to have your own questions for James, so please write those in the chat box on YouTube and we will try and get through as many of those as we possibly can. James, hello, how are you doing? Are you joining us from space?
Hi, Patrick. Really good to see you this morning. Thanks for having me. I'm sorry to let you down. I'm not coming in from space, no. I'm in my flat at the moment in Edinburgh. Not quite as exotic, but I hope you appreciate it's pretty hard to get into space.
Pretty difficult to get into space, yes, but we've got you to explain it all for us today and more about your job. So I suppose let's just start at the start, James, because we've got loads of questions to get through. First question is, what is the Euclid telescope and where is it?
Brilliant. Yeah, so I've actually got the Euclid telescope literally just right next to me here, so I can show you. So let me just take it off this stand. Now, firstly, Patrick, it might not really look like a telescope you've heard of before. I think for most people, when we talk about telescopes, they're telescopes you can look through. This isn't a telescope you can look through. So rather than being maybe in your backyard or in your home and you can put your eye to the eyepiece and you can maybe have a look at the moon or some stars or some planets, this telescope is actually up in space. So it was launched on a rocket, put up into space. So that is really, really helpful for us because when you're looking using a telescope from the ground, our atmosphere, the air, kind of gets in the way. You can still see things, but the air kind of jiggles the light around a bit. And so when you're looking at something in space through our atmosphere, you don't get as clear or a crisp view as you could from space. So that's why building space telescopes are important, and this is one of them. So we call it Euclid. It's named after a Greek mathematician, an ancient Greek mathematician actually from thousands of years ago. But you don't need to know about them. That's the name of it. But this telescope works in the same way as a telescope that you look through does. In the sense that it has a mirror to collect light. So I've nearly dropped it there. If I hold it properly, you can actually kind of look through the center of this cylinder here, this tube. And it does have a mirror like some telescopes that we can look through do. But then this mirror allows this telescope Euclid to collect light, which connects directly to a camera sensor. And then all of this data, all of these images that Euclid can send are sent back to Earth wirelessly. And then there's a team here in Edinburgh that kind of transforms those raw pictures, which look a bit weird at first, into the beautiful pictures that we can see with Euclid. So Euclid is up in space. It's next to a telescope called James Webb, which you might have heard of before. And just to give you an idea of how far away Euclid is, it's about 4 times further away than the moon is from Earth. So it's pretty far away.
That is incredibly far away. And I think we've actually got a video of Euclid or a telescope launching up into space. So we'll see if we can get it on the screen just now, and perhaps you can talk us through it after.
2, 1, ignition, liftoff. Visual propulsion is nominal. Vehicle is pitching downrange.
Falcon 9 has successfully lifted off from pad 40 and throttled down to prepare for max Q, which is coming up at T plus 1 minute.
Power and telemetry nominal.
1 minute.
Cool. Yeah, it's great.
Wow.
It's amazing, isn't it, that we can actually even launch these rockets. And what is amazing about that launch as well is I didn't get to go. I wasn't working on this telescope at the time. I only joined the University of Edinburgh a year ago. Euclid launched on that rocket back in July 2023. So it's been up in space a couple of years ago. But some of the scientists that I work with at the University of Edinburgh, they got to go and watch the launch. I am so jealous. But I imagine for them, that's probably one of the maybe one of the highlights of their career being a scientist, but also maybe very nerve-wracking that this telescope on the is in this capsule, this payload module at the top of the rocket. It's it's designed to withstand the vibrations and the crazy forces that are acting on that rocket. But it must be nerve-wracking for you as a scientist maybe to be standing there and watching everything you've worked on for the past, I don't know, maybe 10 years or longer, preparing that mission, to see it lift off. I think a lot of those scientists must have had their fingers crossed.
Yeah, I was nervous just watching that video, James. So I don't know how they would have felt, if that's all their work going up in space.
It's terrifying. It's terrifying. But yeah, no, it was successful. And so basically with that rocket, it has to have enough liftoff force to overcome the gravity of Earth. And so that's how rockets work. If you can get it going at enough speed to escape the gravity of the pull of Earth's gravity, then you can leave Earth and you can then put that telescope out in space. So yeah, as I said, it's about 4 times further than the moon is away from the Earth. To put that in, again, a bit more context, I mean, no one was on that rocket, no people. No one's going to the Euclid telescope and having a look at it and looking through it or fixing it. But it takes about 4 days in a rocket for an astronaut to get to the moon. So it did take about a week or so for Euclid to be deployed, to be put in this part of space where, as I said, where James Webb is. It's in our solar system. It's just a little bit further away than the moon is.
Wow. I almost need to take a breather because I'm so mind-blown just listening to you, James. I'm sure everyone watching is going to have your own questions as well. So get typing it into that chat box. So we've still got plenty of time to get through your questions as well. So send them in. In the meantime, James, I'm going to move on to my next question for you, which is, can you tell us more about your job? So what part do you play within the Euclid telescope?
Yeah, sure. So I think you introduced me as an outreach coordinator. That is my job title. I'd also maybe say I'm a science communicator. So what that means is that you've got all these amazing scientists who can also talk about their job and what they do. There's about 1,000, 2,000 scientists working on the Euclid Space Telescope across the world, and there's maybe about 10 of them in Edinburgh. But for me, I don't actually do any research. I don't do any maths calculations. I'm not personally studying how things work in the universe like a scientist would. Instead, what I really enjoy is what we're doing right now, Patrick, actually, is just chatting about space. So I want to break down the sometimes complicated maybe maths or the complicated physics or other bits of science that the researchers are working on. And I'm kind of like the middle person, where I get to have lots of fun chatting to people about what's going on. So what's the latest space research? And also importantly is, lots of people in this country pay taxes. So when you have a job, you're paying taxes, and those taxes go towards the government, and they go to all sorts of things, our healthcare, for example. But some of that money goes towards space missions and science. And so people like us will be paying small amounts of money that go into this big pot for science missions. And then the UK does actually play a big role in this mission. And put some money towards it. So what I'm trying to say here is it's really important that people know where their money is going, what it's being spent on. So that's part of my job too, is to really explain what's going on so we all understand where our money's going, but also get the latest updates of the really exciting science that we're doing in this country.
It's so important, and we're so lucky that we've got people like you, James, that are able to explain to us what's actually happening, 4 times further away than we are to the moon. It's absolutely fascinating. It's something that occurred to me while you were answering the last question, James, was you mentioned, there was no people that went up on that launch. So if something happened to the telescope, or if we need to make a change, how do we fix it when it's so far away?
Yeah, we can't. It's a terrifying thing, isn't it? You can't. So I suppose back in the 90s, you may have heard of the Hubble Space Telescope, Patrick. So that's been up in space, I think, 30-ish years now. So it's been up in space about the same age I've been alive, which again is kind of crazy. But that telescope was in orbit around Earth. So we have satellites, these artificial satellites. They're kind of bits of equipment. They could be cameras. They could have other detectors and sensors on. They could give us Wi-Fi or GPS. These satellites that we build are put in orbit around Earth. So that's maybe a few hundred kilometers above the ground. And the Hubble Space Telescope was one of those. So the Hubble Space Telescope was previously, until Webb, Euclid, and others, was our best space telescope. And you've probably seen loads of pictures from it. That could be fixed. That was something we could get to. So quite famously, I think it's something on it was the wrong size. The people building it, the engineers got a bit confused, and it had to be fixed. And so there were astronauts that got sent up to the Hubble Space Telescope and could fix it. That can't happen with Euclid because it is just so far away. And that's why it was so nerve-wracking for a lot of scientists and engineers who put this mission together. Watching it launch, if something goes wrong, that's it. And every day, being in space, space is a very harsh environment. So it's going to be hit by things like meteorites, little tiny bits of rock just flying through space. But it will be designed to kind of not withstand, but if it gets hit by these tiny little rocks, it's designed that it doesn't really impact it so much. It can still be used, but kind of you're right. Yeah, over time, this telescope will gradually get worse and worse and worse. But the good thing is it's designed to map the universe. That's its main job, is make a map of the sky. And I think you said earlier, a third of the sky. That's absolutely right. Maybe a little bit later we can get into the kind of why it's doing that. But that map it's making of the universe is only going to take 6 years. And so in a 6-year mission, it's designed that those little tiny bits of rock that are hitting it, it's not going to affect it too much. But beyond those 6 years, you really will start seeing it kind of get worse and worse. And it is not designed to last forever.
Well, why don't we get into that just now, James? You said, let's go into a bit more detail about mapping the sky, mapping the universe. What does that mean? What's happening up there?
Yeah, of course. Let's do it. So first, there was another telescope called Gaia. And Gaia's job was to map all the stars in the Milky Way. The Milky Way being the galaxy that we live in. So galaxies are like cities for stars. Typically, they contain hundreds of billions of stars. And those, we now know most of those stars have their own planets as well, just like the sun and the Earth. So Gaia was this other telescope that mapped all the stars in the Milky Way. Really useful for people that like space and astronomers and our scientists that are kind of studying space. Euclid is like the next level up. So instead of mapping all the stars in the Milky Way, Euclid is going to map the galaxies in the universe across a third of the sky. So it's a bit of a step up from your OS map or your Google Maps, but it is kind of like a Google map for the universe. Now we say a third of the sky. It can't map the whole of space because in 2/3 of the sky is our own galaxy, the Milky Way. So when we're looking up into space, our own galaxy, because we live inside it, covers most of the sky. But what we can do is we can look at the rest of the sky. We can look at the rest of space, that other third. And in there, we're going to see billions and billions of galaxies. Now, why Euclid wants to do that is it's going to tell us more about some questions we have about the universe that we really don't know the answer to. And that's something called dark matter and something called dark energy. And these two things we really don't know much about. And so Euclid's science goal is to map the universe and help us find answers to, what is dark matter? What is dark energy?
So we'll definitely come on to dark matter, James, because that sounds almost scary and very cool. But I think we've got a video of the mapping that you were talking about.
Oh, fantastic.
Perhaps you can talk us through it.
Yeah, brilliant. Okay, right. Yeah, so here we have a map of the sky. And these pictures that you're seeing here are from earlier this year, back in March, where Euclid looked at 3 small patches of the sky. If you were to hold an apple at arm's length out to the sky, that's about the size of each of these 3 patches that we're looking at here. But as we dive into them, so I think this is called Euclid's Deep Field North, as we keep zooming and zooming and zooming in, start to see not just stars, but every single dot you're seeing there, they're pretty much all galaxies. What we're looking in here is something called the Cat's Eye Nebula. I don't think it looks like a cat's eye, Patrick. I don't know what you think, but something really beautiful there. A nebula, by the way, is a kind of a star-forming region. So out of all of that gas and dust that looked a bit purpley, brand new stars are being formed. But it just gives you an idea, this video, of we've only seen little parts of the universe so far. I said that it's going to take about 6 years to make this map of the universe. We've only seen a tiny, tiny part of it so far. But just in these tiny little patches, you can just zoom in and zoom in and zoom in, and you're seeing all of these little galaxies of different shapes. I don't know if you're able to pause on just that section there. Oh, brilliant. Okay, thank you so much. So it's maybe a bit tough to see, and maybe we'll get onto this later as well. But in the middle, you've got like this bright star on the left. And the bright stars have these spikes. Euclid images, they have 6 spikes on them. And then to the right of that bright star, you can almost see like these curved shapes. And that's something called gravitational lensing, which maybe we can get onto a bit later. But it's one of the illusions of the universe. It's where things like dark matter or heavy things in space are literally bending the light of distant galaxies. And so those galaxies aren't actually curved, but Euclid sees it as these curved, almost slug-like objects because of this effect, this illusion called gravitational lensing. But maybe we'll get into that later, or maybe that's for another day. But that is one of the clues that can help us find out what dark matter is.
The mapping you're talking about kind of reminds me of when you start a new game on, a games console or a computer game or something, and you can only see a little bit of the map, but the further you venture out, the more becomes available to you as you explore. It sort of reminds me of almost
absolutely, yeah. It's kind of frustrating, isn't it? But yeah, in about 6 years, we'll have like 100% game completion, I suppose. Yeah. And sometimes telescope missions can actually be extended, and they can go on longer than they're intended to. So maybe that's like the expansion pack of the game. We don't know if that's going to come. But you never know. But yeah, so it'll be great to see that map just gradually fill in and fill in and fill in. Next year, next October, so yeah, pretty much just under a year from today is when we get the first big chunk of that map. It's called Data Release 1 or DR1. So that's something to look forward to. It's the 21st of October next year. And we should get some really pretty things in that first chunk of the map.
That is super exciting. And I'm sure you've all got your own questions as well. And there's still plenty of time for you to type those into the YouTube chat box. So if you've got any questions for James, get them in just now. James, dark matter. It sounds like something out of a superhero film or a space film. It sounds quite sinister or scary, but I'm sure you're going to tell me that it's not, and it's very cool. Let's get into dark matter.
Yes. I don't know. It's probably, yes. Let's say it's not sinister, but we really don't know what it is. What I would start off by saying is that the universe that we live in and the things that we see every day, so us, people, this telescope, the flat I live in, the trees, everyday life on Earth, everything we can see, and then planets and stars and galaxies and asteroids, all the things that we can see in space with telescopes. All these things that we can see only make up 5% of the universe. And astronomers are great at looking for things we can see because we can build telescopes that collect that light and we can learn more about those things. But there's this other 95%. So most of the universe that we live in, we can't see. It's made of stuff that just doesn't interact with light. So that's why we call it dark. So we just call it dark because we can't see it. Even with telescopes, we can't see it directly. And that's why we call it dark. So we have dark matter. That word matter just means stuff. Like it's physically got like made of something, just like you and me, Patrick. We're made of matter, but we're made of visible matter. There's dark matter out there in space. There was a woman called Vera Rubin. She was an amazing astronomer a few decades ago. She looked at galaxies through her telescope, and she started to notice that these galaxies are rotating. So they're kind of rotating around like maybe a central black hole in the center of the galaxy. She could tell they were rotating just by kind of looking at the light that she was getting through her telescope. But she noticed they were rotating faster than they should for the visible stuff they're made of. And kind of a bit like if you're spinning something on a string, like a conch on a string, if you're spinning it and you're spinning it faster and faster and faster, the faster you spin it, you start to kind of feel the tension in the string. It's working your arm, right? Your arm gets tired, and eventually you're going to let go, and that conch is going to fly off the string because there's no force anymore to keep it tight to the string and pulled and spinning around. So a bit like that with galaxies, the stars in the galaxy are held together by gravity, this force called gravity. And the amount of gravity something has is linked to how much stuff the galaxy is made of, how much matter there is. So Vera Rubin noticed that this galaxy was spinning too fast for the amount of visible matter it was made of. So there must be some missing invisible stuff that's holding it together like glue, or like that force on the string. And so that was kind of one of the first pieces of evidence for this missing matter we call dark matter. But I do have a little demo that I could maybe show you to help kind of show you what that matter is a little bit more, if you like, Patrick.
I would absolutely love that, James.
Okay, so it'll just take a minute. So I'm just going to move my camera here. And I'm actually going to have to put some gloves on. So you're not really going to see me for this demo, but I'm just going to put some gloves on to do this. So while I'm putting these gloves on, let me just say that in front of you on the camera, you should now see this glass beaker. And this glass beaker is going to be our universe. It's full of a liquid. The universe isn't really full of one liquid all holding us together, but let's just imagine that this beaker with this liquid in is going to be our universe. Okay, I've put my gloves on. Brilliant. Safety first. Now I've also got 2 test tubes here. This test tube is our ordinary visible matter. So the stars, galaxies, planets, the things that we can see. I'm going to put this visible matter in our universe. And hopefully, Patrick, you can still see it.
Yep.
Brilliant. Yes. So just like in real life, we can see this visible matter in the universe, the stars and the galaxies, us, planets. Okay. So I'm going to now put in some dark matter. All right. And we're going to put this dark matter into our universe and we'll see what happens. Now, this is just showing that when we use telescopes and we try to look for this dark matter, we can't see it. It's not visible. It doesn't show up in our universe. I don't know, Patrick, can you see that dark matter in the universe at all?
I feel like I can see something, but it's
well,
James.
Yeah, this demo is not perfect. So if you can see something, fair enough. And that's kind of like, Euclid, we with this telescope, we can't see dark matter directly, but you may be able to see like subtle clues of its existence. And that's what we're looking for with Euclid. So you're saying, Patrick, you can maybe just about see that dark matter. I mean, I can put the visible again next to the dark one.
Yeah, when you compare them, that is.
I wonder if did you see that one? That dark matter. Did you see this one? So you can have a bit of fun with it, and if there's time at the end of our chat, Patrick, I can explain what's actually happening and what's happening there in real life. But yeah, it's just a little demo to kind of show, and I'll put myself back on the screen here. That while we can't see this dark matter directly, it's not interacting with light. But there are sometimes you can see subtle clues of it. And one of them I mentioned earlier, it's called gravitational lensing. And it's these little clues that our telescope Euclid here is trying to look for. So we often call it the dark matter detective. because a bit like a detective investigating a crime, it's looking for the clues, looking for the evidence that something's happened or that something's there.
James, you might just need to take over the rest of the session because you've absolutely staggered me there. I'm still recovering from that demo. That was fantastic. Thank you.
No worries. Yeah, it's a lot of fun, that one. A bit messy.
We've still got time for you to send in your own questions on YouTube. So if you're quick, you could answer those. But in the meantime, James, I've got another question for you, which is, I'm imagining there'll be quite a few, James, but what was the most exciting day you've had while working this job?
Yes, I mean, it's a job I love. So as I mentioned, I do love chatting about space. I think there's other elements to my job too. So days like today where we actually get to chat about what Euclid's doing, always really exciting. But part of my current job at the University of Edinburgh involves writing kind of text that can go on social media, on websites, that explains new discoveries. So I think actually I have there was a day in February this year where we had a discovery of something called an Einstein ring by Euclid. So here it is, brilliant. So this is weird, but this Einstein ring discovery was a really exciting day because I guess one of the lucky things about my job is that I get to see these pictures a couple of days before they're released, so that we can write things for the press, things that go on social media, on TikTok and Instagram and Blue Sky, and so that then people can read and understand a bit more about it. Now, this is another example of what I was chatting about earlier, this gravitational lensing. But this is the most extreme example where the light is bent so much by this missing dark matter having loads of gravity, that this is actually just one background galaxy. You might see in the picture, there's 1, 2, 3, 4 points of light that make up this ring. That's just one galaxy, but it's being mirrored and distorted and warped, so it appears 4 times. And I think there's also a zoomed out version of this picture too. So I don't know if we're able to show that, but just sharing this picture, this Einstein ring, was really exciting. There it is. Yes, it's beautiful. So the Einstein ring that we just saw is right at the center of that image, and then there's however many, who knows how many galaxies in that picture too. So this is a really exciting day to be able to share that with the public and see kind of the text that I'd written or put on social media and being shared amongst different people, and see people enjoying this picture.
Fantastic, James. I think we will put a link to All Things Euclid on the Curious About website after this session, so you can keep up to date with All Things Euclid there. We've got time for a couple more questions, James, so we'll get through them as quickly as we can. The first of which is, what kind of skills do people need to work on a project like the Euclid telescope?
Yeah, of course. So a huge variety. It's not just scientists. So if you want to be a scientist, if you want to be an astronomer, then first thing I would say is you want to just do something you enjoy. So if you enjoy doing science and you enjoy doing maths, then maths is a good skill to have to be an astronomer, because we use maths a lot to describe how the universe works. But that doesn't mean that you need to do maths to be involved in a space mission. So for me, for example, if you want to be a science communicator, I do have a science background. So that might be having a degree in physics from a university, but that's not necessarily what you need. I think a good skill to have is just to enjoy talking to people, to be able to kind of maybe clearly describe what's going on. So if you want to be a science communicator, acting is also a route in. If you enjoy drama, if you enjoy being on stage, that's not my route in, but that skill of being able to talk in front of a group of people comes from acting too. And I work with a lot of science communicators that have an acting background but don't necessarily have a science background. But also, there are engineers involved in a mission like Euclid's, who like piecing things together. And again, that might come from a more kind of technical background. It might be a degree, but there's a huge variety of skills, and that's the great thing with these missions like Euclid's. Thousands of people are involved. It doesn't just have to stop at being an astronomer. And I think just being curious about the world around you and how it works, and just having, if you are interested in space or how things work. That's a really good start.
Oh, that's such a fantastic answer, James. Thank you. And yes, my way into working at the Science Centre was also via acting. I didn't feel as if I knew anything about science initially, so there is so many ways in. James, got time for one last question, which is from YouTube, from Tara. Thank you, Tara. If Euclid, oh, what a question, James, to finish on. If Euclid could find anything, what would you like it to find?
Oh, that is a mega question. Okay, so what I personally would like it to find, it's not going to find, which would be signs of alien life. So my research a few years ago when I was doing my master's degree was finding alien life, or trying to find signals of alien life. That wasn't using a telescope like Euclid. That was using a telescope called a radio telescope. It basically is looking for like a type of light that we use for Wi-Fi, for whenever that signal that carries Wi-Fi around, or 5G can also be picked up in space. It's called radio waves. You can pick them up naturally, but you can also maybe look for those types of signals out in space around other planets, around other stars. That might be a good sign that maybe they've invented Wi-Fi, and so might be a sign of an intelligent group of aliens. So Euclid's not designed to look for that, and it probably, we're probably not going to find aliens, but more realistically, what I would like it to find is some more evidence or some more answers for something called dark energy, which is its other thing it's looking for. So dark matter, we said, is this invisible missing mass. Dark energy is this idea that the universe is expanding, and it's been getting bigger and bigger since the Big Bang. Just under 14 billion years ago. And what happens is we see all the galaxies that we're looking at, they're getting further and further away from each other. But the rate at the universe is expanding, the rate at how far and how fast those galaxies are moving away from each other is getting quicker. And we have no idea why. We literally just don't know. And that's what I love about these questions, dark matter and dark energy, is that we don't know. So there are jobs for, in the future to find out these things. So if we could understand a bit more about what dark energy is with this telescope, that would be amazing. I'd love to see that. And it might be in the next few years that we do. So who knows what's going to be in this kind of data release next October, where we might start to understand more about what dark energy is and why the universe is getting bigger, faster and faster and faster. So that would be really cool to see.
Wow, what a way to finish. James, thank you so much from me and from Glasgow Science Centre for taking something so huge and endless like space and making it so understandable and accessible. It's been so nice to speak to you. Thank you.
Yeah, it's been a lot of fun. Thanks so much, Patrick, for having me.
And thank you to you, our audience, for your brilliant questions. If you'd like to find out more about space and engineering, you can find that on the Curious About website, which is curiousabout.glasgowsciencecentre.org. You can also find lots more videos, activities and games on the website, and all of these events are recorded, so if you missed the start or you want to watch it again, this will be available to playback in the live sessions section of the website. Please let us know what you thought of this session. A link to a survey is popping up in the YouTube chat box just now. But until next time, thank you very much and goodbye.